Spectrophotometry is used to measure the concentration of a solution over time by measuring the amount of light absorbed by the solution at different wavelengths. So here you have a light source which produces different wavelengths of light, and this is the spectrometer component, and you have a monochromator which diffracts light into different wavelengths. And the light beam passes through an adjustable aperture and then hits the sample, which is held in a cuvette or tube-like container. Now fractions of the incident wavelengths of light are transmitted and reflected from the sample, and a photodetector, which is the photometry component of the experiment, compares the relative intensity of two beams of light. So you run the experiment once using a reference sample for comparison, and then you run your experiment using your regular sample. And the current from the photodetector is converted into a digital number using an electric circuit where the amplifier amplifies the signal. And the absorbance is displayed on the screen. Now the transmission is the light intensity of the current sample on the light intensity of the reference sample, and the absorbance can be related to the transmission using the logarithm. Now if the spectrometer produces specific wavelengths of light, then it's called the colorimeter. The Beer-Lambert law is used to relate the absorption of light, or absorbance of a solution, to the molar absorptivity, which describes how intensely a sample of molecules or ions absorbs light at a specific wavelength. And the path length B, or the length that the light beam has to travel through the sample, can be obtained from a spectrophotometry experiment. And C is the concentration of the solute or absorbing molecules or ions. Now the path length and the concentration are proportional to the number of absorbing species, but in most experiments, B and C are held constant. So therefore in these cases, the absorbance is proportional to the concentration. Now the Beer-Lambert law is most effective with solutions that visibly change color during the course of the reaction. But if the spectrometer emits UV light, then the Beer-Lambert law can be used to find the concentration of reactants in a solution that are invisible to the human eye. A 0.02 molar solution of an unknown substance A is used to create the following solutions. Now a spectrophotometer is calibrated at 400 nanometers, and the solutions are placed in a cuvette and the absorbance values are obtained. Determine the concentration of substance A in each sample. Well, the first sample fully comprises of substance A and no water, so it has the original concentration. And therefore, the molar concentration is equal to the number of moles of substance A over the volume of the substance in liters, and then from the number of moles, we can obtain a molarity of sample 2. In moles per liter. And repeating this process gives the molarity of the remaining samples. Now what's the molar absorptivity of the substance if the path length of the cuvette is 1 centimeter? Using the Beer-Lambert law and any row in this table, we have the absorbance is equal to the molar absorptivity by the path length by the molar concentration, which gives the following molar absorptivity. And plot the absorbance versus concentration on the given graph and find the absorbance at 0.018 molar. So we draw a line of best fit and read off the absorbance. And you can compare this with the calculation using the Beer-Lambert law with the molar absorptivity from part B.